We continue with another Feistel block cipher, Feistel lightweight block cipher, let's say. It's called CLEFIA, and this is one of the two ISO standards for lightweight block ciphers. So CLEFIA, designed by Sony Corporation, it is ISO IEC standard, which is standardized in 2012. So it is a standard for lightweight block ciphers, together with the present. And the difference is that CLEFIA is a Feistel cipher, present is an SPN cipher. And we can also say that CLEFIA is kind of better choice for software implementations, and present is better for hardware implementations. I'm saying this mostly because CLEFIA operations are designed for bytes, but present works on bits, which is easier to do on hardware. So we believe that Sony uses this algorithm for digital rights management. The block size is 128 bits. It has 3 key lengths like AES. And for this, it has 3 different number of rounds, 18 for smallest key size, 128 bits, 22 rounds for 192 bits of secret key, and 26 rounds for 256 secret key. So as far as I know, the best known attack only breaks 13 out of the 18 rounds of CLEFIA that uses 128 bits of secret key. And it is published in FSC 2007. So the general picture of the cipher is as follows. It is again a generalized Feistel structure, but this time, as I mentioned, the block size is 128 bits. So all these lines actually represent 32 bits. Sometimes we refer to them as words. So this 32 bits is put inside the round function, which is called F0 here and F1 here. They are almost identical with very small changes. You use your round key here and here. There's also a beginning XOR with the whitening key, and then the swap operation. So as you can see, the Feistel structures always look alike, but the only difference is that how you design this round function here. So the F0 and F1 functions of CLEFIA is defined as follows. F0 is here. As you can see, it is almost identical to F1. Let's look at F0 first. So your 32 bits of words divided into 4 parts. So all of these X's actually represent a single byte. You XOR your word actually here with your round key, which is 32 bits here. Then all of these bytes are put inside 2 different S boxes, S0 and S1, which are 8 by 8 S boxes. Then the result is multiplied with a matrix. So this is your output. And if you look at F1, the only differences are as follows. Here you have S0, S1, S0, S1, but here you have S1, S0, S1, S0. So the order is swapped. And also you have a different matrix here. Instead of M0, you multiply it with M1. And if you want to look at the matrices, they are defined like this. So it is somewhat more complicated than height. This is why it provides, in a single round, provides better diffusion and confusion. And for this reason, the total number of rounds are less than height. And this is why it's no cryptanalysis technique has broken the whole cipher yet. So the designers provide some optimization results. So they provide hardware performance here. They compared with the best known result at the time, which is around 2007 actually. So this is not the best AES implementation currently. I'm just putting this picture to show what the designers thought about when they're designing CLEFIA. As you can see, they are using a different technology than the implementation here. So again, it is not easy to compare 2 different technologies, but CLEFIA beats AES in this table. So this is why we believe that CLEFIA is provides better performance on hardware. As you can see, they provide many different optimizations, different ways of implementations, and they focus on the area. They can get as small as, I think, 5,000 gates with good throughput. But when they focus on the throughput, the area actually increases. But since they are focusing on the air speed here, they don't care how many gates they require. So they compare their hardware implementation here, and they also provide the software performance comparison of CLEFIA with AES in terms of cycles per byte. And here actually lower is better, so the results are comparable here. But actually nowadays I don't think that there's much point of comparing a new design with AES on software, because if you are using AES or any other block cipher as a software, most probably you are using Intel or an AMD processor, and all of these processors since 2009 or 10s comes with hardware instruction sets for AES. So you cannot beat those speeds with any software implementation or with any design. So I think nowadays this is not that much important. And as far as I know, some new ARM processors also provide AES instruction set, but we will see in the future how good they are. So, but the main idea is that they design the cipher so that they provide, in terms of key length, provide the same security with AES, but they are kind of faster on hardware. So this is why they became a lightweight standard. So let's move on to present. Now we are moving from Feistel ciphers to SPN ciphers, which is actually the abbreviation for substitution permutation network. A round of an SPN cipher consists of 3 layers: key addition, substitution, permutation. Actually, the order of this key addition from time to time changes. I mean, instead of mentioning here, you can also mention it at the end. It is just a matter of taste, actually. At the key addition layer, we combine the key material with plaintext. So if you have round keys here, you combine it with your plaintext, most of the, or the input of the round, let's say, but most of the time, this is as simple as an XOR operation. At the substitution layer, we provide confusion. Sometimes we use S boxes here, but sometimes we can use different operations like modular addition. At the permutation layer, presence simply permutes the places of the bits, but in AES we perform matrix multiplication, so it depends on the layer you provide, but this provides diffusion. So most famous examples for SPN cipher is AES, which is probably the most used encryption algorithm in the world. But for the lightweight case, present is the best example for an SPN. So in the following slides, I will briefly mention AES, then we will talk about present in detail. So let's look at the picture which I tried to draw for an SPN. So again, we have a plaintext block here. We have our secret key here, and our key schedule algorithm provides us round keys. So we combine our round key with our plaintext block here, then we perform the rounds. So you start with the substitution layer, permutation layer, then add round key. Substitution, permutation, add round key, depending on the number of rounds of your design, you repeat this process R times, and at the end, you provide your ciphertext block. Actually, we haven't talked much about it before, but in terms of security, you can also look at this picture as follows. We claim that the communication channel we are using is insecure, so the attacker always captures the ciphertext block. And from here, even knowing the algorithm, it shouldn't be possible from going from here to the top and obtain the plaintext block, because even if we know all of the details of these operations, because the algorithm is not secret, but the only secret thing is the key. So the person who knows the ciphertext block does not know the key, so they don't know this round key, so they cannot move back here or go and obtain the intermediate values. Even if we tell them what the plaintext block is, so anybody capturing the plaintext block and the corresponding ciphertext block cannot obtain the intermediate values, so they cannot obtain the secret key from here if the cipher is designed in a good way. But if it is not, capturing a lot of plaintext and corresponding ciphertext, sometimes you can break the cipher and obtain the secret key. This is what actually the cryptanalysis is all about. But as far as we know, there are no cryptanalytic attacks so far that breaks present, CLEFIA, or AES. So let's talk about AES for a single slide and then move on to present. We need to talk about AES because it is the advanced encryption standard, so it is standardized by NIST and ISO, so it is like a standard cipher in almost in every country. It was designed by two Belgians, John Damon and Vincent Raymond. The algorithm name was actually Rindel. They submitted to the competition because this was cryptanalyzed due to the short key, so they NIST needed a new standard, and AES won the competition. So Rindel algorithm got the name AES after winning the competition. Other finalists were Serpent, Twofish, RC6, and Mars. These are, as far as I know, none of them are broken, and you can come across these algorithms in libraries like OpenSSL and so on. If you prefer, you can use these algorithms too. So for AES, we have the block size of 128 bits. Key lengths are similar to CLEFIA, but of course CLEFIA is designed later than AES. It supports 3 key lengths. Depending on the security you want, you choose one of them. If you need speed, it is better to use the shorter key because the number of runs is less, which is 10. But if you need military grade security, or if you want to keep something secret for hundreds of years, it would be a good idea to use a longer key. But in this case, you get like a 40% of slowdown because number of runs increases to 14. As far as we know, all of the known attacks are ineffective. This is why we keep using AES. So NIST actually says that in every platform or in any case, if you can use AES, just use AES. This is why NIST actually suggests AES, but they're trying to choose a lightweight cipher because in the cases where you cannot use AES or the even if you can use it, maybe you need more better power or so on, then you might prefer to use a lightweight algorithm. So for this reason, we are having this competition in the first place. So again, we are just trying to focus in this course at the cases where AES is not suitable enough. Okay, so let's look at the present, which is the other ISO standard for lightweight cryptography. So one round of present is pictured here. So it is a very simple design. It just fits at the screen. So the block size is 64 bits. So assume that your plaintext block is here. There are 64 lines here. So every line in this picture represents a bit. Key length is either 80 bits or 128 bits. It depends on your choice. I will mention the key schedule algorithms in the next slide. But regardless of which one you use, the number of runs are 31, and the key schedule algorithm produces 64 bits of round key. So initially you have 64 bits of round key, which is actually the leftmost bits, 64 bits of your master key, regardless of which one you use. So if initially you perform an XOR operation, then you perform an S-box operation 16 times in parallel. So this S-box actually takes 4-bit input and provides 4-bit output. All of the S-boxes are the same. I provided that S-box here. So if your input, for instance, is all zeros, so you have 4 zeros here, In hexadecimal notation, it is again 0. And this table says that if your input is 0, the output is C, which is 12. If you convert the hexadecimal notation to integer, it is 12. But if you convert it into bitwise bit notation, then with the assumption that the rightmost bit is the least significant bit, 12 in the binary notation becomes 1100. So this is the table lookup operation. You perform 16 times in parallel. But as you can see, this provides a confusion, but does not provide much diffusion because these 4 bits only affect the 4 bits at the same place. So this is why you have a permutation layer here, which is just changing the places of bits. For instance, the leftmost bit does not change its place, so it stays at the same place. But this one goes here, this one goes there, this one goes there, and so on. So you are changing the places of the bits. So this is your single round. The output here is taken and fed it again here as the second round input, and you perform this operation 31 times. So as you can see, a very simple picture, very simple operations, but again, it might be hard to implement in software because you need to work on bits, not bytes. So running software code, writing software code for bitwise operations sometimes can be messy, and you can sometimes do implementation errors. This Cipher is also presented at the CHESS conference in 2007. So let's look at the key schedule algorithm. Your master key is K, which is just 80 bits. So we represented every bit with small k. So rightmost bit is K0. As you can see, round keys are the leftmost 64 bits of this master key. Okay, so you are keeping this master key in a register. As a round key, you are always using the leftmost 64 bits, but you're updating this register every round. So initially, the leftmost 64 bits is your round key, but then you take this 80 bits and perform the following operations. Here is the pseudocode. As you can see here, K19 takes the place of K0, which actually means that you are rotating these 80 bits to the right 19 bits. So this is just a rotation operation. Then in the output, now you take the leftmost 4 bits and put it inside your S box and write the output to the same places. And finally, you add a rounded counter to these 5 bits. Round counter means that actually the number of that round. So at the first round, you XOR it with 1. At the round 10, you XOR it with 10. Of course, you write it in the bit notation. At the last round, since there are 31 rounds, you XOR this 5 bits with 31. And if you write this, write 31 in binary notation, what you get is 5 ones. This is why the round counter only affects this 5 bits. So a very simple key schedule, as you can see. There are just a few operations which does not contain much confusion and diffusion, but this is because this is a lightweight cipher. If you add more operations here, your throughput will be smaller. The key schedule for the 128-bit key is not much different, so I also put it here. The idea is the same. You keep your master key at the register called capital K, let's say, and the leftmost 64 bits always represent your round key, but at each round you modify this register. At this time, you perform the rotate operation 67 bits instead of 19 here. You perform the S-box operation again to the leftmost 4 bits, but you also perform the S-box operation to the next 4 bits. So here you have one S-box operation, here you have 2 S-box operations, and again you XOR with the round counter. So the key schedule for the 128-bit is not much different or much slower than 80-bit version, because only difference is that you are performing one more S-box operation, and maybe you require a little bit more memory because here you're keeping 80 bits in a register. here you are keeping 128 bits in a register. So I cannot see the point of using this version when you have this one, which provides a lot more security. Okay, so most of the time I always suggest this version. But I will give an example for this version, which is easier to implement for some reason, I guess. Okay, so here's an example. So assume that we are using the key schedule for the 80-bit secret key, and I chose the 80-bit key, all zeros. So we have 80 bits that are 0 in the hexadecimal notation. This means that there are 20 zeros here. All of them represent 4 bits, which are also zeros. So your initial round key is the 64 bits, left 64 bits of this master key, which is again all 0. Then you perform the rotation operation 19 bits to the right here. But since all of the bits are 0, rotating it doesn't change anything. Then you perform the S-box operation to the leftmost 4 bits. But we have seen in the picture that when the input is 0, the output is C. Then you perform the run counter XOR operation someplace here. So your second round key just becomes this, only this leftmost bit changes the C because there's an S-box operation here. Then you perform the rotation S-box operation round counter XOR again and obtain this third round key, fourth, fifth, sixth, seventh, and so on. As you can see, it becomes a little bit complicated comparing to the all zeros at the beginning, but still you can see a lot of zeros here. This is I deliberately chose all zeros to show you that the diffusion and confusion is not that good in this key schedule, and this is most of the time the case for lightweight designs. Because if you want it to more complicated, then you need to perform more operations, but this means that your cipher will be slower. So if you perform this operation 32 times, we have 31 rounds, but we also had an initial round key XOR. This is why we have 32 round keys. And this is what you get when your master key is all 0. Now, as another example, let's try to encrypt the plaintext block and what happens to it. Okay, so I choose the plaintext block again as all 0. This time we have 64 bits because the block size is 64 bits. And as the master key, I chose all zeros again, which is 80 bits. We already have the key schedule here. We computed the round keys. So what we do is we take the plaintext block, perform key XOR, which doesn't change anything because it is also 0. Then perform the S-box operation. So if you go back to the picture of present, we have all zeros here. We are XORing with the round key. Again, we have all zeros here. So input of all of the S boxes are 0. This means that output of all of the S boxes are C, which is 1100, 1100, 1100 to the end. But we have the permutation operation. As you will see, the leftmost 2 output bits always stays on the left part of the cipher. And the rightmost 2 bits goes to the right half of this picture. This is why the 32 ones that we obtained after the S-box operation goes to the left, and all of the zeros we obtain goes to the right of the picture. So looking at the middle, we have 32 ones here and 32 zeros here. This is why in the hexadecimal notation, after the first round of encryption, your output is Fs here, I think 8 Fs and 8 zeros in the hexadecimal notation, which means 32 ones and 32 zeros. So if you keep this operation going, you will see that after a few rounds, the diffusion and confusion gets better. And you perform this operation 31 times. And at the end, you XOR your output with your final round key and obtain the ciphertext block, which is this. So this means that if you encrypt the all 0 plaintext block with the all 0 key, which is 80 bits version, your ciphertext block should be this in the hexadecimal notation. This is very important because We call these results test vectors. This actually helps us to check if our implementation is correct. In software and the hardware, when we are performing, we are writing code and check our implementations. As you will see, it is very easy to do implementation errors because we are working on bits, and sometimes the operations are a little bit complicated, and encryption algorithms are very different than the codes that we generally write in our daily lives. So for this reason, we have these test vectors to check if we are implementing everything correctly. So if something is wrong, you will see that your round outputs would not be the same as this one, or when you perform the key schedule operation, you will see that when you choose the all zero key, your round keys will be a little bit different from these ones, and you can, with the help of these values, you can check where you're making the mistake. It is very hard to do a good implementation, actually working implementation at your first try. It is really hard to write actual cryptographic code. So here's the hardware performance results from, again, the papers. They compare it with other lightweight designs and AES, and they show that present 80 actually requires 1,570 gates equivalents, which is a lot smaller than the numbers of other ciphers. And they also check the throughput, and they show that they get good results.